how the virtual states show themselves in their chemical reactions. Like before, fact and fiction. The quantum properties of the atoms and molecules don't apply to microscopic objects. There is no home furniture whose drawers become invisible when they are empty. And who wouldn't want it? Who would want it? But the atomic and molecular quantum states are like drawers that are vanished from the empirical world when they become empty, and yet they continue to exist in the system as a part of the real world. Similarly, ordinary objects don't change their forms when you take them out of one room in your house and put them into another. But atoms and molecules do just that. When they change their quantum states, the waveforms that determine their physical and chemical properties change. It isn't only that the electrons in different states are associated with different forms. No, they are these forms. The equivalent at the level of the ordinary thing would be the change of the rabbit into the squirrel when the rabbit hops off the lawn onto the oak tree, and the change of the squirrel into the hummingbird when it jumps from the oak tree into the blooming bush, and so on. When we claim that invisible states exist that are real, we have to come up with some visible evidence, some phenomena that supports that claim. As it turns out, many such phenomena can be found. Among them, the chemical properties of the atoms and molecules. When molecules interact with one another, they can start chemical reactions. In a chemical reaction, the reactions are transformed into products. That is, they become new kinds of molecules. The way chemical reaction proceeds depends on the chemical properties of the reacting molecules, which in turn depends on the virtual state of the reactants. Yes. If the virtual state of the molecule are all high energy states, they are difficult to reach, and such a molecule is chemically inactive. In contrast, when the virtual states of the molecule are lying low on its energy ladders, the molecule is highly reactive. Thus, virtual states affect an empirical property, that is, the chemical reactivity of the molecules. Yes, there is a special class of the reactions. Chemists call them the redox reactions. Yes, redox reactions, in which the reacting atoms or molecules exchange the electrons with one another. Yes. The exchange can lead to measurable changes in magnetic properties, which depends on the virtual state of the reactants. A particularly dramatic example is found in the reactivity of the oxygen. Breathing oxygen can serve your metabolism, because oxygen molecule contains a special category of the virtual states, which chemists call the degenerate states. Because of these degenerate states, oxygen molecules are particularly reactive and can oxidize your food. In contrast, the virtual state structure of the so-called noble gases is such that they hardly react with anything. This is why they are called noble to begin with. Nobility doesn't mingle with ordinary folk. Many other examples can be found that demonstrate their virtual states are real, even though we can't see them, because they affect our observable chemical reactions.